Okay, so good evening. Welcome to the next lecture in the series, the online interaction lecture series of I know project. Today we have Dr. Mehedi Masud. I'll take a couple of minutes to introduce today's speaker. He was an integrated PhD student at HRI, Allahabad during 2009 and 2016. And he did his PhD under the supervision of Professor Raj Gandhi. Many of you must be knowing him as well. His thesis was on the study of CPU violation and mass altering sensitivities at long baseline neutrino experiments. Subsequently, he was a postdoctoral fellow at the IFIC Valencia between 2017 and 19, and currently is a visiting researcher at IOP Bhubaneswar since 2019. His mainly works on exploring various beyond standard model physics, namely NSI, sterile neutrino, Lorentz violation, and so on, at long baseline neutrino experiments such as DUNE, NOVA, and Q2HK. So when we were having last week lecture by Sanjeev, we did mention that this talk would be quite nicely gel with and maybe a little bit like an extension of what Sanjeev was speaking. So thanks again for Dr. Mehedi for agreeing to give this talk today. He is going to talk on landscape of BSM physics in the context of neutrino oscillation at long baseline. Over to Mehedi.
Good evening, everybody. Thanks, Dr. Visete, for giving me an opportunity to present a talk here, and also thanks for the introduction. So today I'll talk about the various beyond standard model physics landscape in the context of neutrino oscillations at long baseline. Am I audible?
Yes, yes, perfect.
Okay, great. Okay, this is the plan of my talk. So first, I will recapitulate some of the basics of standard neutrino oscillations and also highlight what are the pending issues that needs to be resolved. Then I'll mainly focus on three different kinds of new physics, namely the presence of a light sterile neutrino, the presence of non-standard interaction, and also Lorentz invariance violation. And before concluding, I'll just mention briefly about a couple of other new physics. Okay, let's start then. So all of you must be familiar more or less with the basic neutrino physics, neutrino oscillation phenomenologies, etc. So I'll just briefly recapitulate here. So we know that the neutrino flavor eigenstates nu alpha, those are superpositions of the neutrino mass eigenstates nu k, and those are connected by this so-called mixing matrix U. This is the so-called PMNS matrix, and it is a 3x3 matrix in the standard 3 neutrino flavor. Okay, and of course, you know that neutrinos have three flavors in the standard case. There's an electron mu1 and tau. This is a typo. This should be mu. Okay, so we know that the mass eigenstates nu k, those are eigenstates of the Hamiltonian H, and if with this energy ek, and if one wants to find the neutrino oscillation probability, one has to solve this relevant Schrödinger equation, and then find the oscillation probability, which is functions of baseline and energy. Now, this mixing matrix U that you can see that the various elements of U appear in the general expression for oscillation probability. Now, in the standard case, one can parameterize this mixing matrix in terms of three mixing angles, namely θ12, θ13, and θ23, and also one CP phase delta CP. So in addition to these four parameters, the neutrino oscillation probability also depends on two mass square differences, namely the difference of squares of masses of the second and first mass eigenstates and third and first mass eigenstates. Okay, now I'll show the present status of these 6 neutrino oscillation parameters. So there are various groups which does this global analysis and fitting of the best estimated values of these oscillation parameters. And here I'm showing such a fit by this Fourier group. Okay, here you can see that the 6 oscillation parameters have their best estimated values in this second column and their relevant 3 sigma errors in this third column. So among these 6 parameters, theta 1, 2, theta 1, 3, and delta m squared 2, 1, these 3 parameters have been determined quite precisely so far. But the other 3 parameters, namely theta 2, 3, delta Cp, the phase, and the mass square difference, delta m squared 3, 1, so-called atmospheric mass square difference. So their errors are still quite large. And I'll also discuss individually what are the issues relevant to each of these unknown, 3 unknown oscillation parameters. Just to put things into perspective, I have also put here the oscillation probability expression for the nu mu going to nu e case. And you can see that the oscillation probability naively is of the form something like x squared plus y squared plus an interference term. Okay. So the first of these unknown parameters is the Cp phase, delta Cp. You can see that though there is a best fit estimated value of around minus 0.68 pi, its error lies in the whole allowed range of minus pi to plus pi. So it can take any value within this range, which is basically the entire allowed range. And where does this Cp phase appears in the oscillation probability? Now you can see in this interference term of the probability, which we have just shown there as an argument of this cosine, this delta Cp is sitting here. Now, what is the implication of this delta Cp? A value of delta Cp, which is 0 or pi, implies Cp conservation, and a value which is different from 0 or pi is Cp violation. And why is it so important? Because a leptonic Cp violation, that means the value of delta Cp different from 0 or pi, is a necessary ingredient to explain the observed matter-antimatter asymmetry in the universe. So I think we will learn more about this in the next talk of this series by Professor Yajnik. Okay. Okay. After delta Cp, another important undetermined oscillation parameter is basically delta m squared 3, 1, rather the sign of delta m squared 3, 1. What does it mean? Look at this figure. A positive sign for delta m squared 3, 1 means normal ordering or NO. That means, in other words, among the 3 neutrino mass eigenstates, nu1, nu2, and nu3 has the highest mass, or nu3 is the highest active neutrino mass eigenstate. There is another case, another possible case, which is inverted ordering. That means delta m squared 3, 1 is negative, or in other words, the nu3 mass eigenstate that is the lightest active neutrino. So basically, it roughly switches the sign of delta m squared 3, 1, this ambiguity. And you can see that at various places in the oscillation probability terms, this delta m squared 3, 1 and its sign becomes important. For example, this A term, which becomes, instead of 1 minus A, it becomes 1 plus A when one switches the mass ordering, and so on. Okay. Finally, we have another undetermined parameter, which is theta 2, 3. Rather, the octant of theta 2, 3. That means whether the value of theta 2, 3 is lying in the higher octant or greater than pi by 4, that is greater than pi by 4, or it can also be the case that theta 2, 3 is lying in the lower octant. That means less than pi by 4. Now, where does it originate? So look at the interference term again. So you see there is a sine 2 theta 2, 3 term sitting there. So that means whether the value of theta 2, 3 is x or pi by 2 minus x, it has the same value basically. So why are we looking for the octant for theta 2, 3? Because, okay, there are various neutrino mass models available in literature. And in almost all of those models, the octant of theta 2, 3 is an important ingredient in determining the Cp phase. So just as an example, I'm showing here a figure uh, of the allowed region of theta 2, 3 and delta Cp. And this was done in the context of a model based on A4 symmetry. I'm not going into that basically. So just look at the allowed region, which is the green patch here, this green semicircular type of patch. And the x-axis is theta 2, 3, rather sine square theta 2, 3, and the y-axis is delta Cp. Now you see that a lower octant of theta 2, 3 implies Cp violation. That is, delta Cp can never be 0 or pi, basically 0 or 2 pi here. But when theta 2, 3 lies in the higher octant, it can be, I mean, the case can be Cp conserving. Basically, delta Cp can be pi, that means, or 2 pi, that is 0. Okay. So theta 2, 3 is also, the octant of theta 2, 3 is an important ingredient in important input in various mass models rather. Okay. Now, okay. So there are various upcoming new generation neutrino experiments which aim to focus on these three undetermined parameters, and also other physics goals, etc. So here I will discuss about one such upcoming experiment, which is called Deep Underground Neutrino Experiment, or DUNE. So what is DUNE? DUNE is basically a proposed experiment in USA where the neutrinos come from this source at accelerator neutrino source at Fermilab. They propagate through the Earth through 1300 kilometer baseline and is detected at a far detector in South Dakota. And the detector is proposed to have a 40 kiloton far detector with 3.5 years of neutrino run and 3.5 years of anti-neutrino run. So the calculations give it a total exposure of 300 kiloton megawatt year. Okay. Now, in the context of DUNE, I will discuss how sensitive is the experiment to explore the issues related to CP violation or mass hierarchy or octant in the standard case first. Then I will discuss how those standard case capabilities get modified in presence of various new physics. So let us first discuss the first new physics scenario, which is here light sterile neutrino. One light sterile neutrino, which is the so-called 3+1 case. So I think in the last lecture by Professor Agarwala, you have heard a lot of things about the light sterile neutrinos. So I am not going into very much detail of it. So only thing to note here is, so in the 3+1 case, or in case of one, basically in case of one sterile neutrino, there are three additional mixing angles, namely theta 14, theta 24, and theta 34, which characterizes this small mixing with the active neutrinos and the fourth neutrino, which is the sterile neutrino. In addition to these three mixing angles, there are two additional CP phases, which in our parameterization, we have chosen to be delta 24 and delta 34 that I am going to show in a moment. And what are the other? Okay, the mixing matrix U now becomes the 4x4 matrix because of this another new species of neutrino. And the extra mass square difference, delta m square 41, that is of the order of 1 eV square. And it is, I mean, there are various hints from many experiments such as LSND, Minibone, etc., such that the mass square difference lies in that ballpark. Okay. So here I'm just going to show the effect on probability by the presence of the one light sterile neutrino. So what have I done here? So I have plotted P mu E as a function of energy. First, in case of 3+0, which is the standard case in the left panel, and then for the 3+1 case in the right panel. The red line, as you can see from this legend, the red line, yeah, this corresponds to the case where all the CP phases are 0. That is the CP conserving case. And the blue line That corresponds to the case where all the CP phases have some arbitrary CP violating values. And yeah, so as you can see that, and yes, I should also mention that this probability is for vacuum and for 1300 kilometer, which is the baseline of due. Okay. Now you see that when one goes from 3 plus 0 to 3 plus 1, there is considerable difference, considerable modification of the corresponding probabilities. And this difference gets further enhanced when one includes the matter effect by means of this dashed curves. The same levels, but just matter effect is included here. Okay, so this is just as an example about how the new additional phases and of course the new mixing angles due to the presence of 3 plus 1 case can modify the oscillation probabilities. Now we'll see how these probabilities, this modification in the probability that impacts in the level of events. Okay, here I have plotted the nu mu to nu e appearance event as a function of energy, and the left panel is for neutrinos and the right panel is for antineutrinos. And of course, in both the cases, I have used normal hierarchy just as an assumption. The width of this band that points to the variation of the unknown CP phase, delta CP, in the whole range of minus pi to plus pi. Remember, so far this is still 3 plus 0 case, which is the standard 3 neutrino flavor. Now what happens if we include the 3 plus 1 case? So in the 3 plus 1 case, here I have included with these mixing angle values, extra mixing angle values with 5 degrees and 5 degrees of theta 14 and 24. For theta 34, I think we have kept it fixed at a value of 20 degrees. Okay. The thing here is that now this event spectrum band, due to the 3 plus 1 case, that sort of becomes a superset of the 3 plus 0 case, this violet band basically. This is because there are additional CP phases here, and the variation of all of them naturally makes the event spectrum band wider. And what happens if we just increase the value of these mixing angles? Instead of 5 and 5 degree, I have taken now the cases of 15 10 degrees and 20 10 degrees. Of course, you can see now that since the mixing angles have increased, the associated CP phases delta 24 and delta 34, their effect becomes more pronounced, making the band even wider. So you can, for example, for the 20 degrees and 10 degrees case, the event spectrum band is widest here, you can see with the blue one. Okay. The point to note here is the following. Suppose an event lies around this region, okay, in the common region. So then it is not clear whether the event is coming from the 3 plus 0 case or some combination of the parameters in the 3 plus 1 case. So this is one, you can say, a degeneracy between standard case and the sterile neutrino case, which arises, and it can easily be seen in the level of events. So this kind of degeneracy in the sterile neutrino case, that has profound implications in the much involved statistical analysis and so on. So I'll just try to briefly explain one such statistical analysis in the exploration of CP violation. Okay. So before delving into the statistical analysis, let me just briefly say about the chi-square sensitivity, delta chi-square sensitivity. It may be new to many of you. So delta chi-square sensitivity, delta chi-square is a quantity which basically gives you a sense about how two different data sets are compatible. So for example, suppose you have an event data set, n data, which is coming from an experiment. And then suppose you have a theory of your own by which you are calculating n fit by yourself. Now you want to see how the data from the experiment is compatible with your theory. Then you calculate this kind of quantity numerically, of course, and find out the value of delta chi square. If the delta chi square value is small, then you can say that your model fits better with the data. But if the delta chi square is large, then you can say that your model or your fit is less compatible with the experimental data. Okay. And of course, in this kind of analysis, we basically vary all the unknown parameters and publish the most conservative result as our delta chi square, just to be on the safe side. And this variation over all the unknown parameters and taking the minimum of that is the most conservative result. This process is technically known as marginalization. Okay, so just with this concept of delta chi square, that is, it is the measure of compatibility between two data sets. Let us go and see how it gives an idea about the leptonic CP violation capability of Dune. Okay. For leptonic CP violation, what we do is what we did here is that basically we simulated a data from Dune where the CP phase can have any value from -pi to +pi. Then in our theory, we take only the CP conserving values 0 and pi, and then simulate our theoretical data basically, and then find the chi-square between these two different data sets. The result is plotted here as a function of all the CP phase values, and you can see that when the CP phase is 0, the chi-square value, basically the square root of chi-square sigma, that is 0 here, and it progressively increases and it reaches a peak around -pi/2, which is the maximally CP violating value. It is then natural to expect then at maximally CP violating value, we will have the highest sensitivity to CP violation. And of course, then again at CP conserving values, another CP conserving value 0, we get a 0 sensitivity to CP violation. So these things I have also pointed out here, that the sensitivity is 0 at the CP conserving values, and it is maximum at the CP violating values. Now, so this is still the standard 3 neutrino flavor case. Now we'll see how this kind of sensitivity gets modified in presence of one sterile neutrino. Okay. So here, of course, as usual, the black solid line was the previous 3+0 case, and in this green band, I'm showing the sensitivity with these values of the mixing angle in case of 3+1 scenario. And here, since the number of CP phases have now increased, I am now fitting with 3 CP phases, which can have 0 or pi values basically. And the width of the band that points to the variation of delta 24 and delta 34 in the whole range of -pi to +pi. The important thing to note here is that since we now have more parameters to fit in the CP violation, the sensitivity in general decreases compared to the standard case, and this decrease in the sensitivity is quite significant. And this decrease is also depends on the value of the mixing angle chosen, as can be seen in the latter plot. Here we have considered 2 more combinations of the mixing angles, theta 1, 4, 2, 4, 3, 4, with 8, 5, 15, and then 12, 7, and 25. And in each case, the sensitivity band for the 3+1 case gets wider and wider. So it gets very wide at this last case, the blue one, basically. Here, there is an important observation. Let us look at this region. Here you can see that whereas previously we are getting 0 sensitivity, look at the solid black line. Now we are getting sensitivity which is even more than 3 sigma. We can get a sensitivity which is even more than 3 sigma. On the other hand, in this region where we are getting a peak in the case of solid black line, the peak was slightly greater than 5 sigma. But now in case of 3+1, we can have a sensitivity which is even less than 3 sigma. So what we are calling CP violation in the case of standard 3 neutrino scenario can no longer be interpreted as such if one considers sterile neutrinos because of the additional CP phases. And the opposite is also true. That is what we are calling CP violation, basically maximal CP violation cannot be called as such. So this kind of confusion with the, this kind of scope of misinterpretation of the data from those ambitious future experiments, such as Dune, is an important issue to settle with the proper analysis, including sterile neutrinos. And this work was one of the first work that pointed out this issue and has got considerable recognition in the community. Okay, now, so we have now discussed the exploration of CP violation in presence of sterile neutrinos. Now let us go to another new physics, namely non-standard neutrino interaction. And here we will discuss the issue of mass hierarchy sensitivity. Okay. So what is non-standard interaction or NSI? Basically, this is NSI Lagrangian, and it can be both charge current and neutral current. But just to give a very brief qualitative understanding, let us look at this figure. In the standard case, the standard charge current interaction is basically the interaction of neutrino with the electron present in matter. And in the non-standard case, one allows the interaction of neutrinos with, apart from electron, with also up and down quark present in the matter. And this non-standard interaction basically arises in most of the models which tries to explain neutrino mass generation. Okay, I am skipping this. Okay. So from the NSI Lagrangian, one can do some algebra calculations and so on, and arrive at the neutrino Hamiltonian, where now one has 3 terms. Apart from vacuum Hamiltonian and matter Hamiltonian, one can have an NSI Hamiltonian. And this NSI Hamiltonian can be parameterized using these parameters, epsilon, alpha, beta, basically. So this NSI Hamiltonian can have 3 real diagonal NSI parameters, namely epsilon, EE, mu, mu, and tau, tau, and 3 complex off diagonal parameters, namely epsilon, E, mu, epsilon, E, tau, and epsilon, mu, tau. The other elements of the matrix are its complex conjugates. Okay. Now, of course, now you can guess that these NSI parameters are in general complex, the off diagonal ones. So they will give rise to new CP phases. And we'll see how these new CP phases can interfere with the mass hierarchy analysis. Okay, this I have already told. Yeah. So let us first see how the problem of mass hierarchy arises, or what basically prompts one experiment to resolve between the various mass hierarchies, to various mass hierarchies. Okay, so here I have plotted P mu E as a function of energy. The red band is for the normal hierarchy, where the width of the band basically is due to the variation of the CP phase in the entire range of -pi to +pi. The blue band basically is the same, but for inverted hierarchy. Okay. And just to put things into perspective, I have also put in the expressions here. And in the expression, basically these terms which involve delta m squared 3 1, they changes sign. when one goes from normal hierarchy to inverted hierarchy. Okay, let's come back to the plot again, and you see that there is a gap between these two bands, the band due to normal hierarchy and inverted hierarchy. This gap basically is the difference of mass hierarchy, difference of two mass hierarchy, and is a measure of the capability of the experiment to resolve the hierarchies. So you can see that there is considerable gap now in the standard case, standard neutrino flavor case, which we call standard interaction. Let's see what happens when we put in NSI or non-standard interaction. So you see, for NSI, since the variation of the phases now involve more phases, which we call phi mu, the bands get wider and they overlap at some point at many places, and the gap becomes almost becomes very small. So this means in presence of NSI, the sensitivity of the experiment to resolve mass hierarchy decreases. And so this is still in the probability level analysis. And for a full chi-square analysis, one can just look at the full chi-square analysis, the final result. Basically, what we have here is the sensitivity, the chi-square sensitivity to mass hierarchy as a function of the CP phase, for the presence of one NSI epsilon e tau. The black solid line is due to the standard case, and this band, this gray band, is due to the presence of the NSI case. And you can see that the mass hierarchy gets considerably deteriorated in presence of NSI, and this deterioration is even more prominent when one considers a slightly higher value of the NSI parameter epsilon e tau. Okay. So now we have seen how the mass hierarchy ambiguity or mass hierarchy sensitivity arises in the level of probability and how it translates to the chi-square statistics level, and and how NSI basically spoils the mass hierarchy. Now we will go to our third new physics, which is Lorentz invariance violation, and we will discuss about the last remaining issue, theta to 3 octant. Okay. So basically, Lorentz invariance violation, this can be introduced as an effective field theory in a minimal standard model extension or SME. What one does is basically one introduces a parameter, an LIV parameter, Lorentz invariance violating parameter Q, and in the relevant Lagrangian, which can describe the neutrino sector, and when one expands this Lagrangian and only allows the vector and the pseudo vector term in Q, one get this kind of big expression for the LIV Lagrangian only arising from the Q part. So here you can see that the first two terms are basically vector term, and these two terms are the pseudo vector terms. In general, basically one can also allow tensors and pseudoscalars, etc. But here we have just restricted ourselves to vector and pseudo vector considerations. Anyway, so, and yeah, one can basically gather this A and B term and call them together as this, and the C and D term and call them together as this CL. So I'll just jump from here a few steps and go to the final Hamiltonian. So the Hamiltonian due to LIV looks like this. This can also be parameterized like NSI in terms of A alpha betas. And in our analysis, we have not considered C alpha betas, which could also have arisen here. Okay. So one can question what the difference is between this kind of LIV analysis and the NSI analysis we have seen previously. Both of them have very similar Hamiltonian structure. Okay. I have also put the Hamiltonian structure here, and this is the LIV Hamiltonian, this thing, and this is the NSI Hamiltonian, this. So the important difference between these two is, note that the NSI Hamiltonian is actually proportional to the electron density in the Earth. So basically, this is nothing but an exotic matter effect. On the other hand, in the case of LIV, these A alpha betas are we should say intrinsic parameters which may be present even in vacuum. So this important distinction was first shown by Horketius in his paper. Anyway, so with this background, let us now go and see how the LIV affects probability. So as before, we have plotted P mu E as a function of energy, and then with this black line, and then in this red and blue line, we have taken one LIV parameter, A E mu and A E tau respectively, with the same value. And we see that basically A E mu and A E tau affects the standard probability in quote unquote opposite ways. One increases the probability and the other decreases the probability. Actually, when we derive the expression of oscillation probability in presence of LIV, we could see that there is a relative sign in between this A mu term and A tau term, which actually gives rise this effect. And this kind of opposite effect becomes very important later, as we'll see in a few minutes. Okay. Okay. Now I will discuss what octant degeneracy how octant degeneracy arises basically in the level of events. Now, what we did here is, let us just focus only on this first panel and only on this ellipses here, not these blobs, but only on this red and the black ellipses. So this is basically a bi-event plot. So for the CP phase, the standard CP phase is varied, and for each of these variation, one calculates the total appearance event in the neutrino mode and in the anti-neutrino mode and just plots them. So that gives rise to this ellipse. Okay. So basically, along the perimeter of this ellipse, the value of the CP phase delta is different. Okay. And this difference between black and the red ellipse is that, as you can see from the label, the black ellipse is due to LO or lower octant, and the red ellipse is due to HO or higher octant. Okay. So we see that for two different octants, these two ellipses do not overlap with each other. Okay. So that means there is some gap, and this gap basically gives rise to the capability of the experiment to explode between the higher octant and the lower octant of theta 2, 3. Okay. These ellipses are identical in all the three panels. Okay. Now we'll see how what those blobs are. Okay. The solid blobs are the same thing, but now in presence of LIV. In the first panel, we have taken only one LIV, A E mu. In the second panel, A E tau. And in the third panel, two LIV parameters together, A E mu and A E tau. Okay, let's come back to the first panel again. In the because we now have more phases, the variation of the phases will produce a kind of 2D projection of a 3D ellipse, 2D projection of a ellipsoid, you can say, basically. And this becomes these blobs. And the blobs, due to the lower octant and higher octant, they overlap substantially. Okay. So what this overlap mean basically? If you just focus on this region, you can see where there was a gap earlier, now there is overlap. So that means the octant sensitivity becomes can become lost in the presence of LIV. And this is true for individual LIV parameter A mu and A tau. But surprisingly, when two LIV parameters A mu and A tau together, I mean, the lost sensitivity is largely regained. You can see that the extent of overlap, I mean, they do not overlap anymore, the two blobs. This is because the cancellation of A mu and A tau terms because they have opposite signs, as we have seen earlier. Okay. Okay. So here we show, as a consequence of our previous discussion, we show the allowed regions in the delta and the sine square theta to 3 plane in presence of LIV and how it compares with the standard case SI. Okay. The first panel is for SI. So let us focus only on the first panel. Let me explain this. So basically, this is the allowed region at 2 sigma, 3 sigma, and 4 sigma in this delta and theta to 3 plane. So that means if only if a value of theta to 3 which lie outside this, let's say around here, only then the experiment can confidently say that it is indeed lying in the lower octant. But suppose the value of theta to 3 lies around here, around this mouse pointer I am showing here. So here one around here. So here, even if we can say that this is still less than 0.5, this is still less than lower octant, but the experiment will not be able to probe this. Okay. So only the allowed regions basically are this outside of the contours basically. And we see that when one LIV parameter A mu is present, the contours become even wider. That implies that the allowed region, that the ability of the experiment to explore the correct octant of theta to 3 gets even more reduced. Okay. And the same happens for A tau also. But when both of them are present together, A mu, A tau, both of them are present together, we can see that the contours basically again come closer together and come almost as close as in the standard case. Yeah. So that means again the effect of A mu and A tau kind of get cancelled with each other, and one can largely regain the octant sensitivity of DU. Okay. Okay. So far we have seen how the three burning issues of CP violation, mass hierarchy, and octant sensitivity gets modified in presence of various new physics. Now, just before concluding, I'll just briefly mention about 2 or 3 other new physics, which are also discussed much in the literature. So one of them is large extra dimension, or LED. So briefly speaking, the theory is basically a right-handed neutrino. A right-handed neutrino propagates in the large extra dimension, and it couples with active neutrino, providing a Dirac mass term. And there is a process called compactification through which a number of sterile neutrinos appear in this theory. Okay. And the presence of large number of sterile neutrinos basically distorts the probability, as you can see. The dashed line here is the standard nu mu going to nu mu probability. And this distorted probability is basically that in presence of LED with these assumed values of the LED parameter. With this LED analysis, one can try to explore the free parameters such as the radius or size of the extra dimension or the absolute neutrino mass scale, etc. Okay. Another new physics scenario, which is much discussed, is non-unitarity. So in the case of non-unitarity, one can include a neutral heavy lepton or NHL, which of course can arise naturally as an extension of the standard model. And this gives rise to a non-unitary mixing matrix. For example, we have already discussed sterile neutrino. So in the sterile neutrino case, this mixing matrix becomes 4 cross 4, which is unitary, of course, but the 3 cross 3 sector of that mixing matrix becomes non-unitary. And people have studied those and so on. This can also have implication in studying lepton flavor violation. And of course, due to new CP phases, it can have impact on the CP sensitivities. So finally, this is a mention of neutrino decay also, which there are also large number of literatures for neutrino decay. So the theory of neutrino decay can be through a light or massless Majoran emission, and the decay products can be invisible. That is maybe sterile neutrino, or maybe it can avoid detection due to low energies, etc. Or the products of the decay can also be visible decay. For example, can be low energy neutrinos also. Okay. So you can see that there are various new physics theories. I have discussed only 3 of them and mentioned 3 of 3 additional. So the take-home points are these. Basically, in all of the new physics scenarios, there exist additional CP phases. These additional CP phases can have immense implication, basically can give rise to misinterpretation of the data when one searches for leptonic CP violation. Also, as we have seen in the case of NSIs particularly, that it modifies, basically it impacts the mass hierarchy by a large amount, and there is also a scope of misinterpretation. And the same can be said for octant sensitivities as well. So one needs to study more this new physics, uh, especially studying the constraints put on the new physics parameters, so that they are more tighter, more stringent, so that their effect can be minimized, basically. So yeah, that's all I have to say. Thank you.
Thank you. Thank you very, very much. And I think there are quite a few questions on the YouTube, but I also request the participants who are right now on Zoom also raise their hands. So I'll kind of unmute one at a time, and you can kind of ask the question to the speaker. In any case, just let me first go straight to YouTube participants. There are 2 questions from Shailesh Pincha. So let me read that for you. In slide 12, where the expected effects of sterile neutrinos is shown, 3 mixing pretty much coincides with the matter effects with 3+1 mixing. So how can these 2 would be differentiated in experiments?
Sorry, so that again, please.
Shall I read the second one as well? Okay. If large,
yes.
Okay. If large delta chi square implies incompatibility with theoretical data, does maximum chi square, delta chi square, that is 5 sigma at maximum CP in the figure slide 19, mean maximal CP is not supported? I mean, this is the question.
Okay, let me answer the second question first, the CP question.
Second question is slide number 19, it says.
Okay. Oh, sorry, I thought this was the second question.
Yeah. Okay.
Okay, so let me ask the CP question first. Okay, so basically what happens here is you are fitting a data where the CP phase can have all the values along the x-axis, and your fit can have only 2 values, 0 and pi. Okay. So naturally, as one deviates away from these 0 and pi values, the CP sensitivity increases and becomes maximum around plus minus pi by 2. So this interpretation is the following, that when the actual value of the CP phase in nature is plus minus pi by 2, the capability of the experiment to probe CP violation is maximum. Okay. But of course, when the value of the CP phase itself is actually 0 or pi, then the capability of the experiment to probe CP violation is of course 0. Okay. And what was the question about the sterile neutrinos? On slide 12. Hello. Hello.
Sorry. Can you hear me?
Yes, I can hear you now.
Sorry, I just kept it in mute. Sorry. Okay, so that is slide 12, and I'll read out the question for you. The question is, where the expected effects of sterile neutrinos is shown, 3 mixing pretty much coincides with matter effects with 3+1 mixing. So how can these two be differentiated in experiments?
3 mixing coincides.
So
probably.
So 3 plus 0 probably you want to say, but pretty much mixing very much coincides with the matter effects with 3+1 mixing. Presence of
okay, probably no. I'm not sure I have understood it correctly.
Not sure. I hope he's listening to us. And okay. So yeah, he has actually sent another one. For slide 2, I mean to say that at around 2 to 3 GV, okay, the 3 neutrino mixing probability coincides with 3+1 mixing in matter. So can it be differentiated in experiments?
Okay, probably he was meaning this coinciding of this solid line and dashed line, I guess.
Dashed line.
Okay. So both of the right panel is entirely for the 3+1 scenario.
Oh.
So basically, what he meant to say is even in the 3+1 scenario, the vacuum probability and the matter probability with different values of the mixing angles, of course, they coincide at some point. That may happen in probability. So for example, you can say that it can happen at some
later side also,
later stage, later energies also, and so on. So basically, for a full analysis, one has to do a chi-square analysis where the effects from all the energies are included. So even if there is, for example, overlap in a small energy, in an earlier energy interval, I would say, so that can have no longer such overlap in a later energy interval. And if one includes all the energy, the effects from all the energies, energy beams, I should say, then one probably will see that, one probably will get a feel of how much coinciding it is finally, basically. I'm not sure whether I have answered him correctly. Or
he himself updated. So he actually himself updated the question. So I'm sorry I saw it wrong. Actually, the coincidence is in 3+1 case as what you are speaking. Okay. So we'll come back again to YouTube questions, but let me go to the Zoom participant by name Naveen. Has a question. I'm going to unmute. Yeah, please, Naveen, go ahead.
Sir, am I audible?
Yes, you are audible.
So my question is that in standard model, the sterile neutrinos are introduced as the right chiral partners, so that we can have the Dirac-Mayor on a mass term, generalized mass term. But sir, if say there are right chiral particle that we observe the sterile neutrino, so that can the neutrino be purely Dirac neutrino? Or So we can have a purely Dirac field.
Mm, yes, but the nature of whether the neutrino is Dirac and Majorana, that also depends on other issues. I mean, I have not discussed that, but you mean whether the neutrino can be Dirac and it can be detected or not?
Yes, sir.
Yes, in one word answer is yes, but I am not going into much detail into it. I mean, we can discuss later also.
Okay. Thanks.
Sorry.
Hello? Yeah.
Yeah, again it went into.
Okay.
Yeah, I was saying that I'll like to go for the YouTube questions again from Sadashiv Sahu. It says, what are the, this is what, L1 parameters in a normal neutrino oscillation mode, and which of them are violated here? And there's also another question. Currently, is there any event which claims, I didn't get it, L1B, is it? Or what?
L1B or LIV?
LIV, sorry, this is LIV.
Okay.
Sorry,
Okay.
okay, sorry. Exist in nature, sorry, this is LIV.
Okay. So Sadashiv wants to know whether there are any events,
Which
experimental
claims
evidence,
LIV
basically.
exist in nature.
Okay. Okay. Yeah. Okay. So there is so far no direct evidence of the LIV, but yes, of course, there are anomalies which exist in the oscillation data that LIV can explain, in addition to other new physics also. But yeah, so far there is no such direct evidence for LIV. Like, for example, one can get more direct evidence for sterile neutrinos, for example, for the Ellisonian mini-Boone anomaly. Like that, there is no such direct evidence for LIV.
Actually, his first question was, what are the LIV parameters in a normal neutrino oscillation mode, and which of them are violated here? So, and then followed by, currently, are there any events which claim LIV exist in nature? So that was his combined questions.
Okay, okay.
Okay.
So let me go to the LIV Hamiltonian that I have shown. Okay, this is inside.
By the way, in case you're answering, again, there is a related question by him. Is there any correlation between LIV and CPT? It says violence, but he meant
Yes.
violation in bracket if existing in nature.
Yes, actually LIV and CPT violation, those are related. So there is a famous theorem by Greenberg which says that if CPT is violated, LIV will surely be violated, but the opposite is not true. And in the context of the slides that I have shown, so let me go to, let me go to slide 36 here. So basically this is the LIV Hamiltonian. And you can say that LIV Hamiltonian, we have parameterized it to be consisting of two parts, A alpha betas and C alpha betas, which in turn arrows because of this vector and pseudo vector terms in the Lagrangian. And from a detailed analysis, one should be able to see that basically these A alpha betas are CPT violating LIV term, whereas these C alpha betas are actually CPT even LIV term.
Can we also go to Nafis? he asked Nafis Rezwan Khan. He asked for NSI. This is a bit technical, I guess. So let me see. Epsilon E equal to -1 and CP equal to 270, which is close to current global best fit value. There is an exact degeneracy between the two mass orderings. How can this degeneracy be lifted to presence of NSI? In presence of NSI.
Okay. So probably he means this, as I understand, in my slide 25,
Okay.
okay. So this is the NSI Hamiltonian in the square bracket here. So here in the NSI Hamiltonian, in the 1 element, there is this 1 plus epsilon EE. This one arises because of the standard matter effect. So probably he meant this degeneracy which will arise when the value of the NSI parameter epsilon EE is -1. Okay, so that there is a degeneracy between this particular NSI term and this standard matter effect, basically. Yes, yes, this is a quite familiar degeneracy in the literature, basically. And no, so currently we have ourselves also analyzed in presence of LIV and in presence of NSI also. There is currently no way to lift this degeneracy unless except one includes data from a complementary experiment. So for example, one can include data from tune and complement it with data obtained from, let's say, T2HK, okay? Another very high statistics experiment. So with that, there may be a possibility to lift this particular degeneracy with epsilon EE.
Then another question from Syed. It says non-zero oscillation probabilities imply non-zero neutrino masses. In a theory which Lorentz violation, can neutrinos oscillate without non-zero neutrino masses? Hello?
No, for yes, no, no. Okay. For neutrino oscillation to appear, one always have to have non-zero neutrino masses. But yes, what can happen in presence of LIV is that what we are calling the delta M squares, that may be different for neutrinos and antineutrinos. Okay, so this is for the CPT violating LIV. And yes, there are analyses where people have studied how delta M, how the oscillation parameters, they can be different in the case of neutrinos and in the case of antineutrinos due to CPT violation.
Okay. Okay. There's one Supriya. The question is, why did you only consider LIV parameters? Are they nearly zero or others nearly zero? Out of 6 parameters, why did you consider only 2?
Okay. Yes, one can in principle consider all the LIV parameters together. So in this LIV Hamiltonian, but just to understand the physics, I mean, to gain more insight into the physics of LIV, one can take one LIV parameter at a time and see its effect. Now, if you remember, I have already shown that when two LIV parameters, A mu and A tau, are considered together, their effect kind of cancels each other, and one can get a result which is closer to the standard case. But their individual effects are quite large, although in opposite direction. So this kind of physics insight considering the individual LIV parameter gets kind of lost when one takes them together. And this may get even more lost maybe if one considers all the LIV parameters together. So just this is just a reason to get more physics insights of the effects of individual LIV parameters that I have taken them one at a time.
Okay. Dr. Masud, I guess there are no more questions for you. So once again, I would like to thank you for taking your time off and giving this excellent overview of the landscape, as you rightly said, of BSM physics. And what is also nice is that your talks came back to back, yours and Sanjeev. So that actually made kind of the area, the discussion of this particular area complete. So, and also thank you very much for taking each of these questions. And I hope the participants are happy that all these questions were answered nicely. And before I kind of close this session, I would like to also remind all our participants that the next lecture in this particular series is going to be on 20th May, as I was showing on the chat window. And this is going to be on neutrinos and matter-antimatter asymmetry, a unification perspective by Professor Yagnik, Urjit Yagnik from IIT Bombay. So we expect all of you to be back here at 6 o'clock on the same Zoom link. Okay, thank you very much. Thank you also, Dr. Masud, once again. And good night and take care. Dr. Masud, can I close the call? Hello?
Hello? Yes, I just stopped sharing my screen.
Okay. Thank you.
Okay, thank you.
Bye.